So good morning and thank you. It's a pleasure being here, and I thank the organizers for inviting me. I'm a bit embarrassed because basically I'm a kind of amateur in this business. I never wrote a paper on this shape correspondence stuff, and I'm not sure that this is a paper as well. But anyway, the story is that Oren Ben Basat is from the Haifa University. He is a pure mathematician, and he came to us one day and he said, I want to do something applied. So I sat with Michael and Oren and we discussed some brainstorming, and somehow we get to to this issue of point-to-point correspondences. And then Michael continued later to work with all the list here, Dorian, Nogneng, and Max, and Emanuele, which are here, and I met for the first time at the breakfast. So this is one thing. The second thing is the presentation. So there will be, at the beginning it starts nice because this is the slides of Michael. So all the images and everything is crystal clear and nice. And then it starts to be my slides, so it deteriorates and you have a lot of equations and indices and all that. But I had fun, so I hope you will also have some fun of this talk and this result. Okay, so this is the thing. These are deformable 3D shapes, and we would like to classify and say, to be able to say these two are the same and these two are the same, right? So even though they are very in different pose, we would like to be able to say that these are the same object, and this point here corresponds to this point here, etc., etc. Okay. And basically this is not easy because I mean, this is isometric symmetry, but you see that the space of these variations is huge. So this is basically the problem. So what we would like to have is a point-to-point correspondences between two shapes. And at the beginning, I remember, basically my whole knowledge is based on the fact that my colleagues, Ronnie Kimmel and Alex Bronstein, invite me to the exam of their students. So I have to read all the theses or research proposals, and then I know something about the subject. So I remember first that in the GMDS, I think that was the PhD of Alex, or part of the PhD, that was what they did, directly finding the corresponding point between two different manifolds. But today I will talk about a different framework which is based on something else, which is mapping between functions on this manifold, which are mapped to functions on that manifold. Okay, so we have a functional map. This is the name that takes us from this space to that space. And if we have a basis in the corresponding Hilbert spaces, then we can work with coordinates. Okay, so these are the coordinates, and these are the basis of the space of functions. So this is the basis of the Hilbert space in one manifold, and this is the basis for the Hilbert space in the second manifold, and these are the coordinates. The hat are the coordinates in this basis, and the G hat is coordinate in the second basis. And the linear map, if we have a linear map between functions, then in this basis, or in coordinate basis, we have this, transformation, okay, where C is a matrix. Okay, and if we have a set of Q functions like that, and for each one I have the coordinate in this basis and the coordinate in that basis, then for each column here and here I have this relation, so I can write this in matrix form. Okay, so this is basically the type of relation we have if we know the correspondence between, let's say, Q functions here and Q functions in this second manifold. And now we can write down a functional and minimize it to find a good functional map, that map between function on one manifold to function on the other manifold, so the corresponding functions on the other manifold. And basically once we have this, we can hope to find also point correspondences. Okay, so this ends the nice slides, and now I start here. So suppose that I have a map from N to M, a homomorphism from N to M. Okay, so I have this map. Then there is an induced map between the functional space over this manifold to the functional space over that manifold. So how it goes, basically it's very simple, right? So x will be a function on M, and y will be a function on N, right? And f is a function here in L to M, and t applied to f is a function in L to N. Okay. So the question is, what is the value of this function tf at the point y on the manifold N, right? And the answer is very simple. Okay, it's the value of the function at t of y, because I have this map from here to here. Okay, so if I want to know what the value of the function at the point y, I simply map this point to here, and then I take the value of the function f at that point. So basically this map takes a function on M, okay, and give the exact value of f at x, it transports it to y, which is the mapping from t maps from y to x. Okay, so this is very simple. You just move the values of the function to the point, to the corresponding point. So this is the induced functional map from underlying homomorphism or geometric map. Okay. So now the question is as follows. I have L2 of M. I have this Hilbert space, okay, of function. How I relate, how I go from this functional space back to the underlying manifold. Okay, and the standard algebraic way is via maximal ideals. Okay, maximal ideals in the functional space correspond to points on the manifold. And I'll show you how it works. Okay, so an ideal inside the Hilbert space of function over the manifold, the first manifold, is a subspace such that for any function in the ideal and any function in the space, at all, not necessarily in the ideal, but anywhere, we have that the product of the two is in the ideal. Okay, this is the definition of an ideal. And in our case, it's very easy to find ideal that correspond to a point. So this is ideal that correspond to the point, specific point x on the manifold M. Okay, so this is the space of all the functions in this Hilbert space over this manifold that has x as a root. Okay, and clearly this is an ideal because if you multiply by any other function, then at the point x0, this one, at least f will be 0. So the product is also 0, so it belongs also to the ideal. So this is very easy. Yes?
But on the Hilbert space of L2, evaluation at the point doesn't make sense.
What do you mean? I don't get the, sorry, I don't understand.
In L2, L2 consists of equivalence classes of functions, and evaluating at the point doesn't make sense.
Okay, so you can think of this as equivalent class, if you.
Yeah, but then it doesn't make sense because in the equivalence class you have other functions which do not vanish at the point.
Well, maybe you're right. We will discuss that later. Okay.
You need to go to a Sobolev space, or
maybe we have to.
Inequality
Okay, maybe you have to go to a different space. In any case, if we have to have point-to-point correspondence between two manifolds, we have to have a map that maps ideals to ideals. Okay, we cannot have a map, which in principle is possible, that take function from one ideal and send it to two different ideals, etc. So we have to have this correspondence in order to have a point-to-point correspondence. So this is easy to see. Once we have this kind of homomorphism, then the induced functional map is as before, as I showed before. And then clearly, T of I, if I take the ideal and I apply the functional map here, okay, at the point Y is the ideal at T of Y, which is I of X. So it maps, simply follows this equation, it maps ideal to ideal. Okay. So now, once we have a functional map which is induced from a homomorphism, that is a geometric map. Oops. What happened? So when we have a geometric map, then the product, the operation of product between two functions commute with the functional map. Okay? And the product is simply the product of the value of two functions.
Excuse me, but the product doesn't make sense in L2.
Okay, we will discuss
it's in L1.
Okay, so it's not L2. Okay, maybe I'm wrong here and you're right.
No,
so we will go to other functions.
Did you write that if edges are in L2, then the product is in L2? Is that the statement? I don't think you need to.
Well, maybe we can go to other space. It's not the issue here. I mean, if it's not L2 and I'm wrong, then I'm wrong. Then we can go to, we will see what is the right space to do it. But I don't think it's the point here. Okay, so replace everything, everywhere that you see L2N, replace it by other space where this is a legitimate way to write it, okay?
Well, that implication reduces the range of spaces quite a lot. You have
Well, we can discuss it. I'm not sure.
Spaces of
Continuous function.
I mean, in practice, at the end of the day, you do that on triangulated mesh. It's not really such a, doesn't make a difference in practice. But you are right. I mean, if we do it on the continuum, we have to write it the right thing. So we have to think to make sure that this is the right space. But this is not the issue here. This is not the issue here. Sorry?
Or maybe even use a finite dimension. Basically does.
Okay, so basically commutativity, so let's replace, I mean this is wrong anyway, I have a lot of typos here. So replace that with the right space. So here we have two functions in the space of function over M, and this is the product, which belongs to the same space. And then I do the functional map. So this is L2 of N. This is not L2, but this is the functional space over N, should be here. And I can do the other way, do first the functional map, and I get two functions over the second manifold, and then multiply them. And commutativity means that the two ways, I mean this is a commuting diagram, so these two must be equal. Okay? And you can see that if we have a geometric map, then this thing is defined that way, that we've seen before, and this dot is simply the multiplication, and this is back the definition of the functional map. So we have that. This is multiplication pointwise, so this is the multiplication. So if we have a geometrical map, then this map commute with the product. Okay, so this is easy. The necessary condition is easy. The question is it sufficient? Question is whether demanding that this equation is true is enough to have a geometric map underlying this functional map. So if we add up all the conditions that we want from the functional map, and so we want it to be non-trivial, okay, so we don't want everything to be mapped to just 0 or one function. We want it to be linear, of course, and we want it to commute with the product. Okay. So these three conditions actually means that we have a ring homomorphism, and we also have a second ring of homomorphism, which is evaluating at a point. So we take from a functional space to well, I wrote here C, but it can be other field, like the real numbers or something else. So this ring homomorphism just take a function and give the evaluation at a point. And this, well, this is very easy to see that this is a ring homomorphism. It satisfies. It's linear. It commutes with the product, and it's not trivial. And we look on the composition of the two homomorphisms. So the composition of two ring homomorphism is a ring homomorphism. And I'm looking at the kernel. Okay, so I'm looking for all functions in one space such that mapping it to the other space and evaluating it at a point, at y0, gives 0. Okay? And this is an ideal. This is an ideal because of this condition. Okay, so it's clear that this is an ideal, and it's also a maximal ideal. Okay, it's a maximal ideal because here there is no ideal between the 0 and the whole space. So this is a maximal ideal. And maximal ideals in this space, not L2 or in the other space, they correspond to points in M. Okay? So once we have a maximal ideal, we know that there exists a point in M such that this kernel includes all the functions that have x0 as a root. So now we have a position that we start with a ring homomorphism, so commutativity with the product, and we know that for this y0 here, there is somewhere corresponding x0. So we recover that way the underlying geometric map. Okay? So this is very good, but now we have to translate all of this stuff to coordinates. Okay? So now it starts to be messy. Okay. So linearity constraint just mean this thing. So the map of capital phi will be the basis on M on the first manifold, and psi will be the basis of the space over the second manifold. Okay, and linearity just means that there is a matrix here between this basis and this basis. And I also use Roman letters for the basis of the first manifold, and where is it? And I use Greek letters for the basis of the second manifold. Okay. So this is what we need. We actually need what is called structure constants. So I have a product of two basis functions over the first manifold, and this is a function over the first manifold, so I can span it with the same basis. So it gives me this capital A, B, C, which is the structure constant for this basis over the first manifold. And on the second I have the same. I have the product of two basis manifolds over the second manifold in the space of function over the second manifold. And this is B alpha beta gamma psi gamma. Okay, so I span this function again with the same basis, so I have this structure constant here. Okay, now with the structure constant, we can work our way to have a coordinate representation of the constraint that we've seen before. Okay, so this is the constraint, and so now I want to calculate the left side. Okay, so this is the left side. I have to take the functional map of this product. Now this product is this sum. T is linear, so it jumped inside. And then I apply the transformation, the functional map over the basis function C. So it's C at C, and gamma is summed over here. Okay? So this is the left side. The right side, I have this multiplication. So this is a functional map of phi A, and this is a functional map of phi B. So here, this is the transformation of this one, and this is of this one. So this is just rearranging it. Now I have the multiplication, the product of two psi's. Okay? So the multiplication of the two psi is this B here times psi. Okay, so now changing a little bit, okay, I can change beta with gamma here, just to have the same index here. No, I have, okay, this is gamma here. It's okay. So this is 1. So I just take the coefficient. So this is the expression with respect to this basis, and this is the expression with respect to the same basis. So the coefficients must be equal. So this is the constraint that I get in coordinates. Yes?
Do you have a unique representation here after you apply the constraint?
If it is infinite dimensional, then it is unique. I guess the problem is because we truncate in practice. We take only, I don't know, 40 coefficients or something like that. But otherwise, it is unique. I mean, the thing is that these are expansion by basis. If you do a sparsity kind of dictionary, then you start to have non-uniqueness and all the problems that come with that. Okay, so now we can write the objective function. So the first term is just the data term, the fidelity term. Okay, so we have function fp. Okay, discretely we have fi p, right? And the corresponding function gp, which is it goes in the triangulated mesh to gip. I is the vertex index, so it's just the value of the function at this vertex, and this is just the value of that function at this vertex. And the map says give the correspondence. So this is the thing, but usually we work not in the standard basis with delta function 1 at one vertex and 0 everywhere else, but we work in the spectral domain, so we work in the Fourier basis. So the Fourier basis is defined for the shape as the eigen functions of the Laplace-Beltrami operator in both. Okay. And then we have the coefficients with respect to this basis. Okay, so this is a kind of f hat and g hat, and this is a, and this is alpha with respect to the phi and the psi that I showed before. And then in this coordinate basis, we have this constraint. Okay. And this is the second, and this is the constraint that comes from the ring homomorphism. And so this is kind of L2 norm, just square the difference between the left side and the right side. And you see that it is quite complicated. We have quadratic. We are quadratic already in C here, and then we square it. So it's quite complicated thing to minimize. But there are ways to do it in a better way. But I don't know if we will invest more time to do that, but I think there is we can do something like augmented Lagrangian or something to make that work faster and in a more robust way. Okay, so now for the results, and the results are not conclusive. So this part was done not in Israel, and I'll show you the results, and it's a kind of it's puzzling. Okay, so this is first of all about the how we measure the error. Okay, So once we have, well, pi here, I guess this is t. I mean, this is the transformation, or this is the, so this is what we find by the algorithm, the correspondence between that point and that point, and this is the ground truth. And this is the geodesic distance between these 2 points. Okay, this is how we measure the error. And this is, so the red one is this new algorithm, and these are the 2 methods, competing methods, which are here in blue and in light blue, and the dotted is the ICP analog of this method that improve the result. So we see that, and this is for nearly isometric shapes, so we see that here we are kind of doing okay up to that point maybe, and then we are doing worse than the other methods. But the differences are not so big, and you don't see a big improvement using that. And for non-isometric shape, this is this is worse. We are not doing better. Okay. So basically we compare to what Dorian and Max did, and the results are more or less the same, slightly better for small percentage, and worse for non-isometric and for large percentage. And the question is why? And we couldn't understand what actually is the difference between the 2 methods. Basically, I guess we didn't understand the paper that people do before that. So let me go through it, because I think I figured it out. So this is the paper by Nogneng and Otsiannikov, and they demanded that they put this constraint. They said, okay, Cx must be equal Yc, and I write it down here in coordinates because I couldn't figure it out. So I just wrote it down, everything, and this is the thing. So Cx, so this is x. Okay, it's the adjoint of phi, fi, phi b, summed over all over the manifold. Okay, this is like integral over the manifold. And if you write the adjoint here, so this is the thing, this is transpose, and this is area element. So this is really the integral over the manifold. And it is multiplied from the left by c. And yc, so here is c, and y is the same on the second manifold. Okay? And here again, this is basically what you see here. The sum here is integral over the manifold of psi transpose, area element, gk, g, kappa, and psi. And maybe you can explain to me, but I couldn't understand what is the logic, why they should be equal. And anyway, the claim was that this reflects this equation. So if we have a commutativity with the product, then, and we have some correspondence between f and g, then for any other function on the in the functional space over the first manifold, the functional map of the product fh must be the product of tf th. Okay. So let's calculate this this condition. Okay. this is what we have. We have that the functional map of this corresponding corresponding function fp and gp is like that. Okay, so tfp is just so I write f as f hat a phi a. So this is, I write it in the basis and then I apply t. So I get this f hat a c a alpha psi alpha, and I know that this is g of p. Okay. So now let's do the calculation for this constraint. Okay, so we have left side. Okay, this is the left side. We multiply f with h and do the functional map, the t. Okay. So here it is. This is Einstein's summation convention, because I was tired with the sums to write. So here it is. So fp is fa phi a and h is h hat b phi b. Okay. And phi a phi b, okay, is a b c phi c. This is just the structure constant coming here from the multiplication of these two functions. Okay. So I have f hat, h hat, a, and t applied to this phi. So I end up with all this, and this t of phi is c multiplied by c. Okay. And the right side, I do the same. tfp times th, this is gp, okay, because this is the correspondence, and th is h hat b t of fb, so blah blah. Here I get this one. Okay. Now I write gp. gp in the basis, this is a function over the second manifold. So this is g hat psi like that, and then I just copy this factor back here, and now I have two psi. Okay, so I can combine them with the structure constant, and I have cb. So this is what I have here. So now the coefficient of that psi b and the coefficient of that psi b must be equal. And also this is true for any hb that I choose. Okay, so I can throw out hb, or equivalently choose here one for one index and 0 for any other, and I get this condition. So this is the condition I get. Okay, so what's going on? I mean, I did, you know, what is written in the paper. I didn't get the same type of condition as Max and Dorian got. So I was scratching my head. So I went back. I went back to this definition. Okay? And I realized that basically this is the same. Okay, and now I try to explain why. So you see, this is the x. Phi a, this is the adjoint of phi, fi, phi I. Okay, so now let's take f and write it in the other basis. Okay, let's write it in the Fourier basis. Okay, so here it is. So here is the c, is the phi, here is the a, and instead of fi, I just write it in the other basis. So this is f hat phi ci phi bi. Okay, and there is some here over the i's that I didn't write, and of course some over the c's and over the a's, etc. So now look what we have. We have phi a, phi ci, phi bi. Sum over I. This is exactly the structure constant. Okay? This is Let's find here something to write. If I was a physicist, as I am, I would write phi, what is it over there? Phi A. So this is just the inner product of, and in the definition of this inner product is the area element here. So basically, what is written, what Cx means is exactly that. Ca gamma, and I have f hat with the structure constant here. And similarly, for the y, I get the same with the b's. Okay? So now I get basically the equality between these two is exactly this condition here. So basically we are doing the same thing. The only difference is that here you have to have you have a corresponding function to be able to do that. You have to know some f that corresponds to g in the second manifold. Okay, so this is basically the end of my talk. So one thing is that ring homomorphism is a necessary and sufficient condition. Okay, so there is the commutativity with the multiplicity is sufficient, not only necessary, but it's sufficient. So this is an important thing. And we have a general condition. By general, I mean it does not depend on the data. So we have a condition on a map, so on a metric C, that does not depend on the data. It does not depend on the function, the corresponding function that we have or do not have. Okay? It must be satisfied by any C that you find in any other way. So maybe it can be used for any algorithm to improve the map that you find by other methods. And it is equivalent in practice, as we've seen. Well, there are some differences, and I'm not sure why, but we have to see the difference to understand exactly why. It is equivalent in practice, and but because it does not depend on the data, maybe, I mean, we didn't, this is fresh, you know, it's just, we are working on that as I speak, right? So maybe one need, maybe for less, if we have just one function, it's not clear. Maybe when we add more and more functions that we know the correspondence of, then this condition is strong enough. Maybe it's robust. You see that it is linear in C. It's not quadratic in C. Maybe when you have very few functions like that, maybe addition of the more general condition may help. Okay, so these are things that we don't know. We don't know whether using a better minimization technique like the augmented Lagrangian or something like that will give us a better and more robust result numerically. So there are several issues that are still to be understood. But basically, I'm as an amateur, as I said, I'm happy that I was able to understand something. So thank you very much.
Thank you for presentation. We have enough time for questions.
Yeah. Yes.
So if you replace the Hilbert space by a higher order Sobolev space.
Yeah.
I mean, you could encode this by by taking the basis in the Sobolev space.
Okay.
Or you take the basis in L2 and then you would have a weighted Hilbert space with weights which go down.
Okay.
That would take care of that the evaluation at the point
At the point.
does not make
Yes.
sense.
Yes. Yeah. Okay.
This maximal ideal business, it works best with continuous functions and supremum's norm, and there it comes from. That's the Gelfand
Better. Yeah. Okay.
theory.
Mm-hmm.
So the equation that you wrote down for the mapping T, the deviation from being an algebra homomorphism,
Yeah.
you took a Hilbert space norm there because you took a square sum,
Yeah. That's
which means
Mm-hmm.
you are trying to compute a distance in the space of Hilbert-Schmidt operators and not in the space of bounded operators between these Hilbert spaces.
Okay.
Bounded operators, if you view this as a matrix, they have a much more complicated expression, namely it's, what is it? It's the supremum over the L2 norm of the lines. That is
Yeah.
that is the norm.
Yes.
That is the norm
Yeah.
for an operator between
That's the
Hilbert
generalization.
spaces.
Yeah. That's
And maybe if you view this, if you use this as your numerical functionals,
Mhm.
then numerically
yeah, that's a good
errors will diminish perhaps,
Yes. That's a very good remark.
because you have no reason to look in Hilbert-Schmidt operators, which is a very small class of operators between Hilbert
Yes.
spaces.
Yeah. Thank you. That's a very good remark. Yes.
One question: what happens? So basically, you're imposing conditions on the map T or on the matrix C. Basically, that makes it pointwise correspondence. What happens when you discretize the spaces? For example, you don't have the same number of points on M and N. What happens then? How does it become an over-constraint?
This is in the spectral domain. This is in the Fourier already.
Okay, sure.
So I'm not. I don't have this problem of I don't have to have the same number of points. I don't have also to have at the same point. You know,
the
the
constraint-
triangulated mesh. I don't have a vertex go directly.
Sure, the constraint is clear, but then if you try to synthesize the map back in the standard basis,
Mhm.
there is nothing. But let's say if you have the same number of vertices numbered in a consistent way, you would hope to obtain the identity transformation, right? The identity matrix. But if you don't have the same number of vertices, or the area elements are different, then you will never get a matrix that will represent the pointwise map, right?
Yeah.
That exists in the continuous case and doesn't exist in the discrete case.
Yeah.
So how is this reflected in the constraints and the free domain? Do we have an over-constraint problem?
So it's the same problem that
Yeah, we are struggling with this basically for
Yeah.
many years.
yes. So you don't
It would be
have.
pointwise, but not bijective.
Right. Yes,
But still pointwise.
Yes, just one third line.
Any question or comments? So in your talk, you mentioned several times to use Lagrangian to deal with that function. You didn't try it, or do you know anyone who have tried?
We didn't try.
You haven't also.
No,
one have tried about
it's
that.
it's an ongoing. But if you wish to help us, we would be very happy.
Yeah. Most probably the Lagrangian will turn more stable.
Yes. So this is why I said so. You know, it just you have to replace one of the C's in the quadratic term by something else, and then add it as a constraint, and then run everything. So we will have linear equation instead of non-linear equation. Then I think it will be numerically it will be better. So we didn't try everything. This is just I'm telling you the idea, the basic ideas. We didn't finish. This is an unfinished work.
Any other comments or suggestions? Okay, if not, we thank you again.